Team, welcome. We are going to be talking about RC circuit problems, and I want to make sure that you get ready for the PR. So here we go. Let's focus on the first one because we had a lot of issues on this problem last class. So first of all, we have to identify the problem. We see two resistors and one capacitor. Immediately, RC circuit. If it's an RC circuit and it's asking us, hey, find the current at point A, all right, so that means that eventually we're going to come down to the physics of the thing, the problem, and it is the sum of all electric potential. The change of electric potential equals 0. What this means is basically that if I were to take a whole loop around here and I would sum up the change in electric potential or the voltage, which is 9 volts here, for the EMF, and then sum up the voltage across the resistor 1 here, that means that the sum of those will equal to 0. It is also included here for loop 2 over here. Loop 2, we have resistor 1, or the voltage across resistor 1, the voltage across resistor 2, and the voltage across the capacitor. Once you sum those up, it should equal to 0. And you can do it also on the outside. So if you do it on the outside, we include the EMF, resistor 2, and the capacitor. But it's only the loop only touches those that are actually being affected. So since it's an outside loop, it's only affecting R2, capacitor, and the EMF. Okay? All right. Secondly, this is a good to know, because I want you to make sure that you understand that current, when it's summed up, the sum of all current going into the junction equals the sum of all current going out of the junction. So here, in this junction here, because the current is going from positive all the way back to the negative, so it's starting up the top, it hits a junction, which is the red dot. It splits up right here. It splits up right here. And we have current going here and then current going here. And they're different ones. So I2 over here, I1 over here. So it's good to know. That also means that the current 2 is being affected by both the capacitor and the resistor. And we're taking consideration the things that are in the capacitor, for example, like we have to take consideration only current 2 because it is in a parallel. Notice that because we have a split in the current, that means that we are in a parallel. So let me go back here. We identify the current. Now let's identify like voltage across the resistor. So the way that we calculate voltage across the resistor is current times the resistor in question. So pretty soon we're going to be dealing with current resistor 1. So it would be resistor 1, for example. Okay. And the current that it is going through at that moment. So if we're taking and looking at current 1, then if we're looking at current 1 over here, and the resistor 1, so this would be current 1 and resistor 1. Okay? Having some issues with all the coloring. I just want to make sure that you identify all the different things. Okay. And then voltage across the capacitor, we don't actually have an equation on the PRC for that, but it's actually a calculation from the charge in a capacitor. Since it's starting out with no charge and it's slowly charging over time, e to the negative t over RC or tau, okay, resistance capacitance. This one, by the way, the resistance capacitance is the current that is affected by the resistor and capacitance. So in this situation, if we're looking at the capacitor right here, we are being affected by R2 and the capacitance here. But resistor 1 has nothing to do with it. So we have nothing to worry about resistor 1. You don't have to find the parallel or whatever. Just It's only being affected by R2 and capacitance. So that is important for the charge. If we want to find the voltage, we only need to look at our PRC, because our PRC gives us the voltage equals charge, maximum charge over capacitance. They give us this equation because in this equation, they are assuming that the capacitance is completely charged already. And if it's completely charged, time is infinite because it got to all the way up. And this turns into basically 0. And all you have left is, say, this EMF serves as the voltage. This is the same thing. Then capacitance, right? And then the charge. Okay? That is the hypothetical scenario. That's where that equation, this equation comes from. It comes from this equation. Okay? But given that, we can divide by capacitance, like we're doing here, in this equation, and it would give us the voltage across the capacitor over time equals EMF times E times 1 minus e to the negative t RC. Okay, and this is also found on your No, the voltage isn't found on your PRC, but the charge definitely is. Okay, so we have those equations, and those are the important equations that we're going to be needing for this problem. Now, it's asking us to find the current at A. So that means that it's asking us to find current 1 because we label it as current 1. And I want us to first understand, like, what exactly is electric potential. So recall that electric potential. And I know, like, asking you for recall something, all right. Well, I'm trying to reteach you this. So electric potential is really, I know that you know this at least, potential energy over charge. You know that U is potential energy. So electric potential energy over unit charge. If we would put a current or a charge into that electric potential, we would get electric potential energy, because, like this equation says, this is a charge and this is the electric potential right here. You put electric potential and charge together, you get electric potential energy. If we can rewrite electric potential energy as the change in electric potential energy, remember, like the original gravitational potential energy is the same thing. We always go from one point to the other. It is always by a reference. So we usually go the point that is highest minus the point that is lowest. Or in this situation, let's put it this way, B and A, right? And if I'm going from upwards, it's where the arrow is first meeting, right here. And then the bottom is A. So that's why B goes first and then minus A. I wanted to show you this because we've been having issues with that. And then the change in electric potential is the same way. So we would rewrite VB minus VA. That is equal, by the way, to voltage. So I wanted to highlight that because this is important for Kirchhoff's rule. So now let's look at the battery, the first one. And the first one, it's asking us, hey, if we're going to do Kirchhoff's rule, like, is it going to be positive? Is it going to be negative? How do we even identify the EMF on this? So EMF always goes from low to high. Meaning, so we are starting from A, right? If we're following current, we're starting from A and going to B. It's going to be a high electric potential. Usually, if you think about it, once we sum up all the change in electric potential here, it's going to be at 0. Because we sum up all the change in electric potential across the whole circuit, by the time that we get back to the battery, the EMF, or not the EMF, but the change in electric potential is going to be 0. Therefore, A is going to be 0. That's why it's low. And then here, starting all over again, it's going to be 9 volts because the battery is 9 volts. So let's rewrite this. Let's start writing this. If I am following Kirchhoff's loop rule, and I am deciding to take, I'm over here, okay? I am deciding to go clockwise, and I am taking into consideration A, okay? I go, okay, so this is loop 1, and this is my direction. So if I do a little dotted line, and since it's hitting a B first, and then last A, I go, okay, so VB minus VA equals a positive EMF. So why, how is that? Oh, because VB is 9 volts, and then VA is 0 volts. It goes from low to high, and because it goes from low to high, it is positive. That's why we have a positive EMF. But what happens if we decide to be rebels and decide to go, okay, let me just take loop one and go counterclockwise instead? Oh, that would really piss off my teacher. Okay, well, not really. That's cool and all. It'll make your life a little bit more interesting, but it's basically okay. So you're starting on now from A, VA minus VB, because again, it's where the arrow is. So like we go on the arrow hits first A, and then, well, it hits here A, and then if you look at it, BB is last. So that would be a negative electric potential because we have VA is 0 minus 9 volts. That would equal a negative 9 volts. Okay, so follow the arrows. Follow that, like do this if you have to. Notice where the arrow is at and then do the calculations from there. Like batteries always go from low to high. Meanwhile, segue, resistors always go from high to low. So in this situation, the current that we're interested in is, and this is incorrect, let me just erase this, this current 1. We're interested in current 1, and current 1 is over here. This is current 2. Right here, this is current 2, this is current 1. Okay, since we're interested in current 1, and we're looking at that direction, and following direction, like let's just do the little lines that I've been showing you. Okay, so from here, okay, so it's D first, and then going to the end of the arrow is C. So that means that VD minus VC equals negative voltage across the resistor, because resistors dissipate electrical energy. It dissipates electrical energy. Because it dissipates electrical energy, thus it affects the voltage, the change in voltage, decreasing the change in voltage. That's why we have a negative electric potential, negative change in electric potential for the resistor. Okay, so just to wrap it up, since we're trying to find the current at point A, we have current going here, and then we have our loop, I1, we have our loop going around. I'm going clockwise because like it's always best to follow the direction of the current. Whenever you can, just follow the direction of the current. Okay, and then I will rewrite this. The electric change in electric potential equals 0. The sum of electric change of electric potential equals 0. EMF, we're counting that, minus the change in electric potential of the resistor. Remember, it's going from high to low, so I'm putting a negative here, 0. And then I'm going, okay, so I am solving for minus I1 times resistor 1 equals 0. And finally, I1 equals the EMF over R1. And if you get 0.05 amps, you are good to go. If I missed the signifigs, and I'm sorry, don't get on my case for it. All right, just Just like, yeah, this is the answer overall. Okay, and we move on. Just for the heck of it, let me just put a 0 here. We are good. Let me double check because I know that you guys are sticklers for sig figs. Because I am a stickler too, unfortunately. All right, we are good on the sig figs. Okay. Now we are at part B. So part B, I have a diagram here because I want you to see this. So like it's 0.5 seconds. Let's calculate the current after 0.5 seconds. And remember what I said, that the current in I2 is the only one that's actually being affected because it is going straight to the capacitor. Okay, but current 1 is not being affected at all because current 1 is on a completely different level. If you go into your lab 1 app where it shows like where you were playing around with the circuits and how to do it in simulations, you'll see you can build this and you can see that even though current slows down immensely over here in current 2, in current 1 it continues flowing. It is not completely closed off. Okay, that's the beauty about having a parallel circuit. Like you can continue, like even though the current is completely frozen here in I2, I1 is still moving. So one thing that's important for I2 is this one. It's, look at the diagram on my right over here. The current, once we start the timer, from 0, it is completely high. It is at the top. But once we continue, it starts decreasing. The current starts decreasing in I2 because of the capacitor. Meanwhile, the capacitor is getting fully charged. The capacitor is getting fully charged here. And as we have seen that V equals charge over capacitance, as charge increases, you can bet your butt that the voltage is also increasing. So we are on a good to go no basis. We know that current is changing in resistor 2 as well. Not so much resistor 1, but you will see it wouldn't really matter. Like as long as you follow Kirchhoff's rule. Okay. Let's continue on. This is another way to see the circuit. I just wanted you to see, at least notice that the current over here, current 2, see, like it's only being, like current 2 is the only one being affected by the capacitor. Current 1 is by itself affecting only R1. Okay? And that's another way to see the junction. You see, like it's very deceiving. I know it's very deceiving, but once you get back to it and you redo it like this, you're like, oh, okay, I can see that there is a parallel circuit involved. Okay. All right. Enough mumbo jumbo. Let's go and finish this problem. Okay, so if we are looking at solving only for the current 2, because current 2 is in B, let's go on the other edge. I think it's best because if not, we're just, it's not really hard to do it. If you do it this way, loop 2, loop 1, and then loop 2, trust me, you'll get the same answer. Let's just go loop 2 completely. So let's go in steps, and this is for Matthew. I told Matthew that you have to derive to solve for the current. But there's actually an easier way to do this if you just follow Kirchhoff's rule. And if we go and say, okay, so the sum of all electric potential equals 0, and then we start taking into account everything outside the loop. So EMF is still positive because we're going in from low to high, positive. Then the resistor, voltage across the resistor. So voltage across the resistor, oh, but this time current is changing, therefore the voltage across the resistor is also changing for the resistor. So we can write over time, and let's just write our little r over the bottom to just know that it's voltage across the resistor, resistor 2. And then we go, okay, so the voltage across the capacitor is also changing over time because it is charging. Now, after that, there's nothing else that we have to worry about. Why is this negative? Well, it's because, again, it's like the resistor. Capacitors work from high to low. Since they go from high to low, like the resistors, they follow the same thing. It is also negative if we're going in my clockwise direction. Okay? Okay, so now let's finish this off and write, okay, so 0 equals EMF minus I2, I2 over time times R2 minus EMF 1 minus e to the negative t over RC parenthesis. Now, this is the voltage across the capacitor. This is the voltage across the resistor. Notice that I have the current over time here. But also notice that EMF is here and EMF is here. If I multiply the EMF here, right, and I have, let me just rewrite it just so you can see this, because I know like I take my time, I know, and some people get frustrated, but I need to explain this because then you're like, oh, but how did you do that? Well, here it is. You multiply this together, and then there's an EMF here too, sorry. All right, you multiply the EMF with the equation, and now you can cancel this and this. This is still equal to 0. And then we can bring this to the other side. Notice that if you remember the derivative of charge, or the derivative of charge is actually the equation that you're seeing right here. But now you don't even have to derive. You just did Kirchhoff's rule, and voila, you get the actual equation that you needed without ever deriving. And I know that you hate deriving. I hate it too. So this is a very simpler way of doing it, or at least visualizing it. Just taking into account all the voltage across the resistors, across the capacitors, across the EMF, and then summing them all together, and you get the same thing. Now, the only thing you have to do is substitution. The current at 0.5 seconds for current 2 is equal to 5.5 times 10 to the negative 4 amps. And that is your answer for this part. Oof, it was all doozy, but we got it done. Okay, so now you remember time here. Time here would be time 0.5. And then the resistor would be only the resistor 2 because it's the only one being affected by the capacitor at that moment. And then the C for like the actual capacitance of the capacitor. Team, for problem 2, which you have to do by yourself, I'm just going to give you a couple hints. You have to use Kirchhoff. You can't use, let me write it down, Kirchhoff's. You can't use resistors in a parallel because you have the capacitor here. Whenever you have a capacitor and resistor in this form, it gives you the hint that you cannot by any means do resistors or by resistors in parallel or capacitors in parallel. Now, if you had an example like this, where you have series here, a resistor here, resistor 1, resistor 2, and then you had right here. Then you had capacitors in parallel. Then that would mean that resistors, the equivalence for resistors is R1 plus R2. And the equivalent for capacitors would be C equivalent equals 1 C1 over 1 over C1 plus 1 over C2 to the negative 1. And you would find the resistors are equivalent and the resistors, the capacitor is equivalent. That is the only way. Whenever you see something to this effect, like this, there's a resistor here, then you can't just find the equivalent resistor or capacitor. That changes the game completely. It goes into integration, and it's nasty. You will never see a problem like that. However, for purposes of practicing Kirchhoff's, this is actually a pretty easy problem if you just tackle it in Kirchhoff's loop rule. 1, 2. Or understanding that current here, current 2, changes over time, and current 1 does not, because current 1 is not stuck by any capacitor. Okay? All right, moving on. All right, so this is a pretty simple problem. It is basically about a capacitor that is charging at time 0. So read the problem for a second and let's tackle this. First thing that you want to do is always write down the equations, physics. The sum of all change in electric potential is equal to 0. Our awesome charge equation our voltage across the capacitor equation, where it says that at max charge, Q equals, now voltage across the capacitor equals charge over capacitance. And then our voltage across the resistor equation, where it equals I current times the resistance of that resistor. Now we do the solve. And we're saying like, hey, it moves from point A, and actually it moves from point B and goes to point A. And we have to do an analysis and calculate the current across the resistor. Now notice too that this diagram is a series. Because it's a series, as we're doing the loop, and this is completely, it doesn't matter because it's not connected to anything. Since it's a series, that means that our current is constant. So even though we're saying current through the resistor, it could very much well be current in any other place around the circuit. So we can write down, let me change my color, V minus, right, because we're going for Kirchhoff's, voltage across the resistor minus voltage across the capacitor equals 0. EMF minus ITR, which is current across the resistor, or voltage across the resistor, I'm sorry. And then EMF 1 minus e to the negative t over RC equals 0. And then we have e over R negative t over RC equals IT, which is current over time. Now I have it set up right? I have everything set up. It is basically the same format. And at the end of it, you should get this equation. That equation is going to equal to 0.943 seconds, right? Like the timing that we're calculating. And that will equal to 6.67 times 10 to the negative 4 amps. If you didn't exactly have this answer, and maybe I'm the one that incorrectly did the calculations, at the very least, if you have this equation, you are good to go. Okay? Good. Because remember, in physics, we care more for the process than we care about the answer. In this one, it is very simple. Instead of you focusing on charging, notice now that it is discharging. So what is the equation for a discharging capacitor? And analyze from there what is the current at 0.943 seconds. And finally, this one. So for those of you that already seen this video before and are going through it again, you'll notice that I changed some things. This problem is actually extremely hard. And it is because we have two capacitors and resistors in parallel. Unfortunately, we cannot solve these in, like, if we had a time, let's say that we have a time 0.5 seconds, we wouldn't be able to solve the current at position B, because you're having this resistor affect the current of both I1 and I2, but then you have another resistor here that is affecting the current as well. And then you finally have the capacitor. These two capacitors are not charging at the same rate. Because they're not charging at the same rate, it complicates the equation. You can start off doing Kirchhoff's rules and it would be, you would get far enough, but then you would have to do other integration. So for simplicity, part B, I am going to change to time equals 0 to find current. Now, for the sake of training, I am going to analyze here what would happen if I only had resistors instead of capacitors. Actually, I'm going to erase this. We're actually going to have to do this, but let's imagine that we had only capacitors in this parallel. So just imagine that the way that we would solve for this is 1 over capacitance equivalence equals 1 over C1 plus 1 over C2. And that's how you would solve for the equivalence capacitance. In this situation, because time equals 0, our voltage across the capacitor, if you notice, 1 minus e to the negative t over RC, that's our equation for voltage across the capacitor. Notice that this goes to 0, or this whole thing goes to 0, and e to the 0 is 1. 1 minus 1 is 0, so voltage across the capacitor is 0 at time 0. Therefore, our capacitors, capacitor 1 and capacitor 2, are not actually required. Instead, what we need is to solve for just the resistors. So in this situation, we have resistors in series and resistors in parallel. In order for us to get the current at A without ever doing Kirchhoff's and just relying on resistors in parallel and in series, remember, the only reason why we're doing this is because the capacitors have no input on this because the capacitors are 0. Therefore, the only thing that the circuit is registering at time 0 is the resistor 1, resistor 2, and resistor 3. So I'm going to put it right here. In order to simplify our matters, and instead of trying to find a different currents, we can just do a jump and consider these 3 resistors as one equivalent resistor, and that would be the equivalent resistor is equal to R1, R1 plus parenthesis, because now R1, say R1 is a series, and we want to convert R2 and 3, which are in parallel, into one equivalent series, one equivalent resistor for us to consider. So -1. All this will equal to resistor 2, 3. And now that this is combined and resistor 2 and 3 become one resistor, we can now sum up the equivalent resistor, the total equivalent resistor of the circuit, to R1 plus R2 and 3. That should equal, resistor equivalent, to 150 ohms. And that should be your answer for the resistor equivalent. Now that you have that, it is very easy for us to solve for current in the actual just solving for, let me see, it says voltage across the resistor equals current at point A times resistor equivalent. And that resistor equivalent, you can multiply, actually you have to divide. So you have to divide voltage across the resistor over resistor equivalent, and that should give you 0.80 amps. So now we go to part B, which I will leave for you. Now, in this situation, I am going to, instead of 0.5, because it won't be able to work, let's do it again with 0.0, which means that you don't have to use the capacitors, but you know how to use the capacitors, you just don't have to use it here. They cancel out. So the thing that you have to do in this situation is do Kirchhoff's. So in Kirchhoff's, you do have to find the current across that junction, and you also have to do Kirchhoff's loop around and maybe inside the loop too. That's an option, just as long as you understand the capacitors are canceled because t equals 0. Okay, so I'll leave you to it. I hope this video is helpful. If you have any questions or if you find any errors, please send me an email and I will try to clarify, and I will continue updating these videos. I have to give special thanks to both Connor Bishop and Annika King for finding some errors that I was able to correct it immediately and basically update this video to ensure that you're successful in the WPR. All right, well, let me know if you need anything else, and good luck.